I don't want to do this again. I got so close the last time, but here we go. So this video covers electron configuration and the quantum mechanical model, plus a few extra little things. So first we're going to start off with a brief history of the atom. So Dalton was the one who first said that atoms are indivisible particles. And then J.J. Thomson came along with the plum pudding model, which showed positive and negative charges scattered throughout. And Rutherford was the one who said that atoms have a dense positively charged nucleus, and then Bohr realized that because electrons don't spiral towards the nucleus, they must orbit it. And so here is the Bohr model, which shows an electron in the ground state. And then the Lyman series and the Balmer series illustrates electrons dropping down from the excited state back to the ground state. And when this happens, a wavelength is emitted, and that can be calculated using the Rydberg equation. And we'll do a hopefully quick example of this, of an electron dropping from n equals 4 to n equals 2. And so 1 over the wavelength equals the constant, which is 1.097 times 10 to the 7th times 1 over n final, which is 2 squared, minus 1 over n initial, which is 4 squared. And that number is here. And then that is only 1 over the wavelength, so to calculate the actual wavelength we have to do 1 divided by that, which is 4.863 times 10 to the negative 7th meters, or 486.3 nanometers, and that is a blue wavelength. And so from there we can look at the absorption and emission spectrums. Absorption spectrums show which colors are absorbed and have black lines where the wavelengths are emitted. And then the emission spectrums obviously here show which colors are emitted, and this is that of hydrogen. And so we know now that the Bohr model is only valid for hydrogen, and this is because of the Heisenberg uncertainty principle in part, which says that you can never know both the exact location and speed of an electron at the same time. And also Hund's rule, it's such a rule, not law, which says that electrons fill orbitals one at a time before doubling up, making pairs. And so that brings us to the quantum mechanical model, which says that electrons do not have fixed orbitals, but rather exist, or they don't have fixed orbits, but rather exist in orbitals in the electron cloud. And using this, we can write out electron configurations, which show the distribution of electrons in those orbitals, which are S, which has 1 orientation, P, which has 3 orientations, D, which is the double dumbbell, and 5, and then F, which has 7. We can also write out the quantum numbers. N is the principal quantum number, and it shows the size, and it's usually or always the period number. And then L is the angular momentum quantum number, and it shows the shape. M is the magnetic quantum number, and it shows the orientation. And then S is the spin number, and it's either, the electrons are either spinning clockwise or counterclockwise, so it's either positive 1/2 or negative 1/2. And then we have time for one quick example. So we're going to do sodium, and you can look at any of the periodic tables around the room. And so sodium is 1s filled, and then 2s is filled, and then 2p. And because of Hund's ones, we fill in 1 at a time before doubling back, and then 3s, which just has 1. So writing out the electron configuration, it would be 1s2, 2s2, 2p6, and then 3s1. And if we were to write the quantum number for, say, this electron, the N number would be 3, the L number would be 0, the M number would also be 0, and because it's an S block, and then the S number, since it's pointing up, is +1/2. And I think that's it, and I am just over time. Sorry, Miss Enlow.